Hi everyone, this is Anand and today we will be discussing the problems and solution of CodeDrift. Hi everyone, so today in this video I will be discussing the problem coin stacks. So let's first go through the problem. So the problem says that meanwhile Erlich was tricking Big Head by playing a game of coins with him. There are two players in this game who play the game turn by turn. There is a pile of A coins and in each turn the player can remove a certain number of coins between 1 and B. Okay, so basically there are two players A and B, and there is some pile of coins. Okay, like let's say this is some pile of coins. Okay, and in each turn the player can remove certain number of coins between 1 and B. Okay, so there is a pile of A coins. Okay, and from that pile of coin the player can remove any number of coin between 1 to B. Okay, let's say if there are, let's say A is equal to 10 coins and if B is equal to 2, then you can remove either 1 coin or 2 coin. Okay, you cannot remove 3 coins. Okay, or it's also not possible that you didn't remove at all, so you have to remove either 1 coin or 2 coin. Okay, now the player who cannot move anymore loses. Okay, so Erlich decided to move first and set the values of A and B beforehand in such a way that ensures his victory. So Erlich will be moving the first, right? Now Guilfoyle, watching this from far, got tired and decided to help Big Head from getting tricked. So he told Erlich if he moves first, Big Head gets to decide the value of B. Given that Erlich will always move first, help Big Head find different values of B so that can he guarantee his victory. Okay, so the problem says that it's given that Erlich will always be moving first. We need to choose value of B such that Erlich will be not Erlich, the second player, which is Big Head. Okay, which is Big Head will be winning. Okay, so there are two players, Erlich and Big Head. Okay, Erlich will move first. Okay, and what we have to do, we have to set a value of B. Okay, so that given A piles, Big Head can always win. Okay, we have to set such a value of B such that given some value of A, Big Head will always win, or alternatively you can say that Erlich will always lose. Okay, so we have to count how many such values of B are possible. Okay, and whatever are the possible values of B, we have to also return it. Okay, so now let us look at the example. Okay, so now we know that we have to choose those values of B which guarantee the victory of the second player, or alternatively which guarantee the loss of the first player. Okay, for example, if you say that, let's say there are 2 coins in a pile, and if you choose P is equal to 1, then what happens is that if there are 2 piles like this, okay, what you can do, the first player in the first move will remove one coin from it, and the second player in his move will remove the remaining coin from the pile, and after that the first player will not be able to move, so the first player will lose, or you can say the second player will win. So B is equal to 1 is a possible value of our answer which can guarantee the victory of the second player. Similarly, B is equal to 2. If B is equal to 2, then what you can see, what the first player can do, the first player will simply remove all the coins from this pile. Okay, because after that the player B will be left with no coins, and so the second player will lose. Okay, so B is equal to 2 is not allowed, right? And similarly, any value of B which is greater than 2 will not make the second player win. Okay, for example, if you choose B is equal to 3 or B is equal to 4 or 5, so any value which is greater than 2 cannot ever make the second player win, because what will happen is that the first player will always select all the coins from this pile and the second player will be left with no coins at all. So that's why we will never be choosing any value which is greater than or equal to A. So even choosing B is equal to 2 will make the second player lose. Okay, similarly, if you take the example like this, let's see, let's say if A is equal to 6. So for this case, the answer is only B is equal to 1. Okay, for the previous case where A was equal to 2, the answer is only one thing, the answer is only 1. Okay, so there is only one value, so we'll simply return only one value which is equal to 1. Okay, now let us look at the second example. So let's say in the second example, our A is equal to 6. Okay, which means there are 6 coins in our pile like this, 1 2 3 4 5 6, okay, 6 piles. Now let's start choosing the value of B. So let's say we choose B is equal to 1. So B is equal to 1, what the first player will do, it will take one coin in its turn, the second player will again choose one coin in its turn, the first player will again choose, the second player will again choose one, the first player again chooses, the second player again chooses. Now the first player is left with no more coins, so the first player will lose and the second player will win. So B is equal to 1 is one possible value which guarantees our winning. Okay, similarly, if B is equal to 2, then what happens? So if B is equal to 2, okay, if B is equal to 2, then what we can do, let's say if B is equal to 2, okay, if B is equal to 2, then what we can do, like you can see, like if the first player, let's say, chooses only one coin, so it will remove this one. Now in the second player, what the second player can do is that it can remove these 2 coins. Then in the third move, the first player will, it doesn't matter that whether it removes 1 or 2, there always remains either 1 or 2 coins in the pile, so the second player can remove those coins and the first player will be left with no coins. So the first player will again lose and the second player will win. On the other hand, if the first player chooses the first 2 coins, okay, if the first player chooses the first 2 coins, okay, then what the second player can do, the second player will simply remove only one coin from it, and then the first player will choose. It doesn't matter like whether it chooses one or it chooses two. The second player will again be left with either one or two coins, which ultimately he can remove all of them, and the first player will again be left with no coins. So in both the cases, like again, it's the second player who will win. Okay. Similarly, you can try for b is equal to 3, b is equal to 4, b is equal to 5, and for b is equal to 6, you know that who will be winning. Okay, it's actually the first player who will win, because if there are like six if there are like 6 coins and you have set your b to be equal to 6, so the first player will simply select all the coins from this pile, and the second player will be left with no coins. So you know that the second player will lose. Okay, so we don't need to check for this. So if you just calculate for all the values of b who will be winning or losing, you will find that there are only 3 values at which the second player will be winning, which is equal to 1, 2, and 5. Okay, like for 5 you can see like why it is so, because if there are six coins like this, the first player, doesn't matter how many coins he chooses, like if he chooses one coin, then still I am left with 5 coins, which the second player can remove all of them. Similarly, if he chooses even the 5 coins, then still I will be left with one more coin, which I will remove. Okay, by I mean the second player will remove, and ultimately the first player will be left with no coins. So in that case also the second player will win. So these are the 5 values which we will return. Okay, so now let us look at the approach for it. So before heading towards the approach, let us think of a simple question, that given some a and b, how do we know whether the current player will win or lose? Okay, so the current player wins if and only if there exists some way, that is some number of coins, by choosing which he can ensure the loss of the second player. Okay, so what it means is that there must be some number of coins between 1 to b, such that if he chooses that many coins, then he can ensure that the second player will lose. Okay, loss of the second player. So obviously the loss of the second player is the victory of the first player, right? Or the victory of the current player. Okay, so this is the condition for winning. Okay, similarly, when will the first player, or when will the current player lose? So the current player will lose if, irrespective of the number of coins he chooses, which means irrespective of how many coins between 1 to b the current player chooses, the second player, or you can say the next player, is always going to win. Okay, so if this condition happens, then obviously the current player will be losing the game. Okay, this is also called a losing state, or you can also call it a winning state. Okay, so let us define a function f of a comma b. Okay, so f of a comma b will be equal to 0. Okay, if the current player loses or 1 if he wins. Okay, so let's say f of a comma b is this much. Okay, so for finding f of a comma b, let's see this thing. Okay, so if we want to find f of a comma b, so if there are let's see one thing, that if there are a coins, okay, if there are a coins like this, okay, so what the second player can do, the second player can either select 1 coin from it, 2 coin from it, 3 coin from it, 4 coin from it. Okay, or he can select at most b coins from it. Okay, so if he selects 1 coin from it, then we got something like f of a minus 1 comma b. If we select 2 coins, then we got something like f of a minus 2 comma b. Okay, similarly for 3 coins, a minus 3 comma b. Okay, similarly you can also keep on finding like this. Okay, so so if this is like the first player, if you consider it like a first player, okay, and this is so the next move will be done by the second player. Okay, so when will this value be equal to 0? Okay, by 0 I mean that this current player, or you can say the first player, will be losing. So it's better to write it like current player. Okay, so let's call it to be current player, and let's call it to be the next player. So when will be the current player losing? So if its value is equal to 0, then means he will be losing. So he will be losing if either of these things, okay, if either of these things is equal to, not either, like if all of them are equal to 1. Okay, because as I said earlier that the current player will lose if and only if, irrespective of the way I move, the next player is always going to win. So if the value of all these things, so f of a minus 1 comma b, f of a minus 2 comma b, up to so and so up to f of a minus b comma b, because I can remove at most these many things. So if all of these things, okay, if all of these things have the value equal to 1, then my value will be equal to 0. Okay, on the other hand, when will I be equal to 1, which means that when will I be equal to when will I be in a winning state? So I will be in a winning state if one of them, okay, if one of them is equal to 0. It might be possible that 2 of them are 0 and let's say the rest are 1, but at least there must be a single one. It should not be the case that all of them are equal to 1, because if that's the case, then I will be in a losing state, or f of a comma b will be 0. There must be at least one 0. Okay, maybe here or maybe here, anywhere, right? Out of these b possibilities, so these are like the b possibilities. Okay, there must be at least a single 0. Oh, okay. Okay, so let us try to make a table for finding the value of a and the corresponding whether the player will be winning or losing. Okay, so let us say that we took our b as 5, and let's see the effect of changing the values of a, and how the winning and losing condition changes with varying the a if b is constant. Okay, so So let's see. The first thing is that let's say if a is equal to 0. So if there are no coins, then obviously the first player will always lose. Okay, so this will be equal to 0. Okay, similarly, if there are only one coin, if there is only one coin, and since b is equal to 5, so the first player will, or you can say the current player will select all those one coins, and so he will win. So this is equal to 1. Similarly, if a is equal to 2, so these are the values of f of a comma b. Okay, these are the values of f of a comma b as defined earlier. Now for a is equal to 2, again the first player will win. For a is equal to 3 also the current player will win. For a is equal to 4 also it will win. For a is equal to 5 also it will win. And now if you go to a is equal to 6, so for a is equal to 6, okay, so the current player can choose any number of coins from 1 to 5. Okay, so if he chooses one coin only, then we will be left with 5 coins. Okay, now we know that this is a winning state, so whichever player will be choosing the coins in this state will be winning. So it means that if the first player choose one coin, the second player will guaranteed to be winning. So what the first player will just try avoiding choosing one coin. Similarly, if he chooses, so this is the case for choosing one coin. Similarly, for choosing two coins also it is losing. Okay, for 3 also, for 4 also, for 3 also, for 4 also, and for 5 also. Okay, so that's why the player with a is equal to 6, so if a is equal to 6, the current player will be losing. Okay, similarly for having a is equal to 7, okay, a is equal to 7, the first player will be winning, the current player will be winning. Okay, so alternatively what you can see, as I discussed that f of ab is equal to 0 if all of f of a minus 1 comma b, f of a minus 2 comma b, so all the previous b values are equal to 1, and it is equal to 1 if one of those previous b values contains at least 1 0. Okay, for 7, so for 7 you consider these previous 5 values. Okay, these previous 5 values 1 2 3 4 5, you consider these previous 5 values. So you see that these previous 5 values has a 1 over here, a 0 over here. Okay, it contains a 0 over here, so that's why it is equal to 1. Similarly for 8 also, you will consider these previous 5 values. Since it contains a 0, it will again be a 1. Okay, similarly you can just keep on filling, for 9, and then for 10 also it will be 1. Okay, and for 11 also, for 11 also it will be 1, and finally, no, for 11 it is, yes, for 11 also it will be 1, because you simply check the last 5 values, which will be equal to like this. So these are all, not all ones, there is a 0 over here, but for 12, it will be equal to 0, because like all these previous 5 values are all ones, it will be 0. Okay, so this is the observation. So what you see is that, like, it forms a kind of pattern. Like you see that a 0 initially, then like 5 ones, right? 1 2 3 4 5 ones, then again a 0. Okay, then again a 0, then there are like 5 ones again. Okay, so these are like consecutive 5 ones. Okay, these are like this one, this one, this one, this one. So it kind of form a pattern, right, where if you start varying your a with 0, then it forms a pattern like this: 0, then 5 ones, then 0, then 5 ones. Okay, and more interestingly, what one thing you see again is that so we want to make our final objective is to make the second player win. Okay, so what we want to do is that we want to choose our b in such a way. Okay, so we know that a is already fixed. Okay, a is already fixed, so we need to choose a certain value of b such that f of a comma b becomes equal to 0, because we want the second player to win. So if the second player wins, it means the current player or the first player will be losing. So f of a comma b should be 0. So let us check that at which possible values of b a is coming to be equal to 0. So you see that when we fixed our b to be equal to 5, then we see that for a is equal to 0, f of ab is 0. Then for a is equal to 6 also, it's 0. And similarly for a is equal to, or you can say a is equal to 12 also, it is 0. Okay, so it means that if you are fixing a value of b, then the second player will be winning at a is equal to 0. Okay, then b plus 1, then 2 times b plus 1, and so on. Okay, and so on. As you can notice also that here b is equal to 5, we had said b is equal to 5, so I was the second player was winning, or the first player was losing at a is equal to 0, then 5 plus 1 6, then 2 into 6 12. Okay, so you can notice from here also. Okay, so now we know. Okay, so now we know that given a value of a and b, given a value of, so if when we fixed our b, so a would be losing only if and only if a is equal to either 0 or like 6, not 6, basically b b or like b plus 1, actually b plus 1, b plus 1, and like, or like 2 times b plus 1. Okay, or 3 times b plus 1, something like that. Okay, so you can also say that a should be equal to some multiple of, let's say, k times b plus 1. Okay, or from here what you can also see or what you can also say is that b plus 1 will be a factor of factor of a, right? You can also see, or you can also say like that, right? So since we are given a value of a, what we can do, we can just find all the factors of a. Okay, for example, if a is equal to 10, then all factors of a will be 1, 2, 5 and 10. Okay, and just equate it with b plus 1. Okay, so if you equate b plus 1 with 1, you get b is equal to 0. If you equate b plus 1 with 2, you get b is equal to 1. Equating b plus 1 to 5, you get b 4, and equating b plus 1 to 10, you get b is equal to 9. Okay, so these will be the four values of b for which f of a comma b will be equal to 0, or alternatively the current player will be losing and the second player will be winning. But as you can see that you cannot set b to be equal to 0, right? Because we need to choose some positive value of b, right? So that's why we cannot just allow this one, because at the end we need to choose some number of stones, or you can say coins, from 1 to b. So b cannot be 0, b has to be at least 1. So we will simply remove this one, b is equal to 0 is removed, or simply you can say that you find all the factors of b, okay, and remove 1 from it. Okay, you remove 1 from it, because 1, if you cannot just allow this one, because then it will lead to b is equal to 0, which is not allowed. Okay, so for example, in this case, since a was equal to 10, I will be the current player will the second player will be winning at b is equal to 1, 4 and 9. So we will simply return this, right? So if I just explain you through the example which I gave you earlier. Okay, so the earlier example, if you see, okay, so this one, like in this case also, you can see that here a was equal to 6. So if you find all the factors of 6, this will be equal to 1, and 1, then 2, then 3 and 6. So you don't consider this one. Now you simply subtract 1 from it, because these are equal to b plus 1. So b will be equal to 1, 2 and 3. Sorry, 1, 2 and 5. 6 minus 1 is 5. So 1, 2 and 5. Okay, so and you can see also that this was also the same thing that we got earlier. Okay, so that's it for this. Now let's see the pseudocode for it. So let's say we had some function which will return let's say some vector of integers. Let's call it find, and let's say it accepts an argument like a. Okay, so we first try to find all the factors of a. So let's say we declare a vector for storing all the factors, or you can say all the possible answers. So we just iterate for int I is equal to 2 lesser than or equal to a I plus plus. Okay, so you know that for iterating over all the factors of a, basically we need to iterate only till the square root of a, and if we know that some number I divides a, then we also know that a by I will also divide a. Okay, so that's why we just iterate over the till the square root of a. So we check that if a divides I. Okay, and let's make I to be equal to 1. Okay, so the first thing we check is that if a is divisible by I. Okay, we now check that I should not be equal to 1. So if I is not equal to 1, then we push in our answer, push back I minus 1, right? So this is the first thing we did. Also we check the other factor. So the other factor will be equal to a by I. Okay, but we must ensure that a by I is not equal to a, right? So we first check, like if a by I, if a by I is like not equal to I. Okay, then we just simply push answer dot push back like whatever is this thing, a by I minus 1. Okay, and at the end we just close this for loop, and finally we just return the answer. Okay, now coming to the time complexity part. The time complexity of this approach is order of square root of a, because we are just iterating through all the factors of a starting from 1 till square root of a, and there can be like around square root of a iterations, and so the time complexity of this approach will be, so the time complexity of this will be order of square root of a, right? And the space complexity will be order of square root of a. Now the reason why space complexity is order of square root of a is because since we are iterating over square root of a values of I, and in the worst case what can happen is that you will be having like, either you just, if a modulo I is equal to 0, then you answer you push back in the answer I minus 1, or you, if a by I is not equal to I, then you push back a by I minus 1. So at most there can be at most 2 times square root of a elements which can be pushed to your answer, because we are iterating over only square root of a times, and in each time we are pushing some element which is equal to I minus 1, and that also 2 times, right? One time I minus 1, another time a by I minus 1. So that's why this complexity will be order of square root of a. Okay, although there exists some tighter constants also on the space complexity, because if you notice that you are only pushing the total number of factors of a. Okay, the number of elements which are being pushed in your answer is basically equal to the total number of factors of a minus 1, because we are excluding 1, and there is a tighter bound on the number of factors also, which is equal to cubic root of n, cubic root of a. Okay, so you can also say, so this is a tighter bound on the space complexity part, that it is order of cubic root of a. Okay, so I hope it's clear to you, right? Thank you. So if you enjoyed the video, please like, share and subscribe our channel. Thank you.